So welcome to this tutorial on MATLAB. In this video we will see how to use MATLAB and some of the functions that will be useful for this particular course. So I am Shomokanti Mahapatra, one of the TAs for the course. So let's get started. So whenever you open MATLAB, you will see a interface something like this. So here to the left you can see this is the current folder. I'll come back to this later. Similarly, you can see a command window in the middle, and there's a workspace to the left. And you have different tabs like home, plots, app, some things like this. So to start, actually you can do almost everything from command window. So like I can add two numbers, so like 1 plus 2, that gives me 3. I can multiply two numbers, but it's not very good practice to use the command window as you have to every time type everything you want to get the results. So it's better to write it in a file. So to do that, you click this new script button and this editor window opens up. So here you can do the same things, like I can do, suppose I want 1 plus 2 and then to execute this file, you need to press this run button, or you can press F5. But remember, we need to save this file before we can run this. So to save it, you can see there's a save button. I'll press this and I need to give it a name. So the name can be anything, but it can't have any spaces and it can't start with a numeric value. So I'll just give it a name test for the time being. So now if I run it, you can see the answer is 3, but now I can quickly change one of the digits. So I want 3, and now if I run it again, you can see the answer changes, and it's much more convenient to use it. And also you can see that this test file is now saved in this current folder. So this current folder is basically the folder which contains the file which you are running. So whenever you have file open, you can have different files open in this editor window, but whenever you press run, it will always it should be, I mean, that folder, it should be open. So even if you are in a different folder in this particular one, you can when you press run, there will be a pop-up which will show that you need to change the folder, and you can press that button and directly go, or else you can press this particular button and then navigate to that particular folder you want. Okay, and so similar thing. So this is MATLAB, the installed version in a PC. So similar things you can actually also use MATLAB's online version. So the MATLAB's online version will look something like this. So this is the particular website, but you need to log in to get into this, and it works almost exactly same, except a few heavy duty functions and other things. You can do almost everything you want inside this particular MATLAB online version. So now let's see one of the file which I created. So this is just some basic things. So at first, so these at the top, these two functions, they are mostly called housekeeping functions. So what they do is they will clear this command window. So you can see the command window is kind of clogged. So if I want to clear it, actually I can just type CLC, it will clear the command window, as you can see. And the workspace also will get filled up with the values to the variables you are assigning. So you can also clear the workspace so that function is clear. So that's why I have just added these two at the beginning of the file, of this particular file, so that every time that happens. Okay, now let's start with some basics. So suppose I want to assign a number to a variable. So here it is a, so I can assign it as 3. So this semicolon at the end, what it does is, so if I don't have this semicolon and if I run it, you can see that output is shown in the command window. But if I have a semicolon at the end, what will happen is the output won't be showed in the command window. So it is means you can selectively see whichever one you want. So similarly, you can use pi. So pi will be very much used in the in some of the calculations. So p, if you type just pi, it will actually be the value of pi. You can see this value of pi, and whatever value is being shown here, even if the output is not shown, so like I'll hide the output, but still the value of the variable is being stored. As you can see, this is the value. So if you open it, you can see the exact whole value of pi, whichever it is taking. Okay. And similarly, I have c, which is 2, and I can do some kind of addition and subtraction operations like this. Similarly, I can do a times b, which is like multiplication of scalars, and I can do division like a divided by c. So this is like 1.5. So it was a by c, so 3 by 2, this is 1.5. Okay. So these are like scalars. So if you want to raise to the power, so this is just directly you will use this symbol and then to the power the number you want. So like it is 3 to the power 3, so it is 27. If you want the exponent function, so e to the power something, so you need to use exp and then in bracket then a. So actually, if you want to see it, so like if I start typing, suppose I want to know what, so start typing, so you can see that the function, some of the functions which starts with ex, it will automatically show. So I will suppose go to exponent exp and then in bracket, so it will show that okay, I can input some of the values I want, whichever one is defined previously, I can put one of them. So it is much more helpful. I mean, it will provide you help while you are typing. Some of the functions, there are actually 2 arguments. So like one will come later. So a tan 2. So if I now give the bracket, you can see there are actually 2 arguments. You need to give y and then x. So it will help you while you are typing it. Okay. So now coming to a few trigonometric function. So like you can do sine of pi by 3, but here remember this is sine function, this is in radian, and if you want to input the values in degrees, so you need to use this sine d function. Similarly cos d, tan d. So actually I'll show you both of them, s1 and s2 actually give the same value, but the inputs are in different formats. Okay. Similarly tan 45 is 1, so you can see this is 1. Now inverse cosine function, inverse function. So similarly here the output can be 2. So this AC1 and AC2, so both of them have the same input, but so first one will give you the value in radians, so this is actually pi by 2, and the second one will give you in degrees. Okay. Now a tan, just normal a tan is like tan inverse, but it's the basic one, like just y by x. So if you have a point like -1 comma -1, which is in third quadrant, and you want to find the angle made by it with respect to the x-axis, that will be -1 divided by -1, so it will be always 1. So you will see that this value is pi by 4 actually. It won't. So if I do it a tan d, you can see this is 45 degree. Okay, but suppose I want the exact coordinates also, means like exact quadrant also while calculating a tan. So then what you do is you take a tan 2. So there actually it will see that okay, y, so this is actually y and this is x. So it will see that okay, both of them are negative, so this should be in third quadrant, and you can see this answer is in -135. So this is actually in third quadrant. Okay. Similarly, logarithmic functions are also there. So this is just natural log. So this will be like ln3, and if you want to the base 10, this is like this one. So log to the base 10. So this is how it's done. So most of the functions you which you will use, so you can get help from MATLAB itself if you want to know much more about it. So for that you just type HELP, then in space you give after giving a space you give the what is the function you want to know about. So suppose I want to know about log 10. Okay, so if I press enter, you can see that it will give out the help thing. So it will tell you that okay, x is the input and how you are supposed to give the input. So like x is complex results are produced if x is not positive. Yeah, because logarithmic functions we always consider greater than 0 values. Similarly, you can do like you want to know more about 8 and 2. So you can see that okay, every detail is given, and similar things you can actually also do it online. So like suppose I want to know more about plots. Okay, so there's a function in plot. So if I go to plot and MATLAB, you can see you can go to this particular link and then you can see different arguments and different input things you can tweak around and change, and there are a few examples also which you can try it out. And here also you can search for different functions and you can see much more about them. So like this is eta and 2, and there are some examples also given provided here. So I would highly encourage you to use these ones, and there are also other files, websites which provide help from which you can use actually. So we highly encourage you to search online and explore the other possibilities of using these functions. So this was more or less about the basics of the MATLAB, how it looks and how it works. Okay, now we will go over a few examples of in linear algebra, right? So I'll go line by line to tell you what is happening in this particular file. Another thing is, so if you have a percentage symbol in a line, so whatever is after that percentage symbol is treated as a comment. So MATLAB will not execute that particular thing. And actually you can comment whole sections of, like if I want to comment this whole section of, I can just directly select it and you can see this particular button. So this will comment this whole thing. And similarly, if I want to uncomment it, I'll just select it and then press this one, it will uncomment. You can do it by Control R and Control T also. Okay, so the basic thing is scalar. So like this is 2. So if I run it, you can see the value is 2. So now if I come to vectors, so vectors will be like kind of two types. So it can be either row vector, it can be column vector. So the row vector is in this form. So you will start with a square bracket and you will also end with a square bracket, and then you can have the elements. So the elements needs to be spaced either with a space, physical space, or you can do it by comma. So if I run it, you can see that okay, this A1 is 1, 2, 3, but if I have commas in between them, it will also detect the same thing. So either comma or space will work. But if you have a column vector, you need to separate the elements by a semicolon. So you can see there are semicolons, and if I now run it, you can see it is in a column format. Okay. So similarly in matrix, you need to kind of combine these two both. So like the rows will be in the rows, it will be space, means the elements will be distinguished by space or comma, and then if you want to go to the next row, it will be like changing the row. So you will use a semicolon, and now suppose if I run it, you can see this is okay. This is 1, 2, and 8 on top, and then 7, 5, 6 on bottom. Okay, we can also concatenate two matrices or vectors. So here actually I am concatenating A3 and A1. So like A3 will be on top and A1 will be on bottom. So you can see that if I run it, you can see this top part is A3 and this is A1. But please be mindful that the dimensions of the vectors being concatenated should be consistent. So if I actually change it to A2 and I now run it, you can see that it will show error, and actually it will show that okay, what is the error is? It is the dimensions of arrays being concatenated are not consistent, and it will show you the which line has the error. So line 12. So if I click it, it will actually go to line 12, and you can see that what you have made the mistake. So it is very helpful. MATLAB also provides you help when you have an error. So suppose I now want to transpose a matrix. So for transpose, you will use this single quotation mark, and you can see that okay, A4 was this and A5 is this. So actually if I increase a little bit, you can see that okay, yeah, it is exactly transpose. So the 7 goes to 2 and similar things. Okay. Now if you want to type identity matrix, you can always type it out like 1 0 0, then 0 1 0 and so on. But you can use this function EYE, then provide the number. So this number will give you what is the dimension of the matrix. So this one is an 4 by 4 identity matrix. So you can see it here. Now you can also find the norm of a vector. Norm is like L2 norm, the magnitude of the vector. Okay. So you can see that okay, we are taking the norm of A1. So A1 is 1 2 3. So it is doing something like square root of 1 square plus 2 square plus 3 square. So this is how it's done. So similarly, cross product. So cross products, you can see that we are having the cross product of A1 and A2. So even though they are, one of them is row vector and one of them is column vector, it can manage. So and please be mindful that in cross product the order of multiplication matters. So A cross B is minus B cross A. So and similarly dot product. So you can see that it does the dot product for you. You can have determinant also. So suppose if I wanted to find the determinant of this matrix A4. So this is how you do it, DET, and in brackets you put the argument. If you want to find inverse, there are two ways. So you can do INV, then the argument, or you can directly do some A4 to the power minus 1. So it will also work like that. So you can see both of them actually gives the same value. Okay. Rank. So rank also works in a similar way. So suppose I wanted to find out what is the rank of A3, this one. So this is a 2 by 3 matrix. So it can be a maximum of rank 2. So you can see that okay, rank is 2 here. Okay. So now rotation matrix. So rotation matrix you will be using extensively in this course. So you can actually type out in that form, like, so rotation matrix X will be like 1 0 0, then 0, then cos theta sin theta, then 0, then cos theta, then minus sin theta, something similar like that. But you can directly use a function which is provided by MATLAB. So it will be like ROT, then the axis you want to rotate about. So this is like X, and then by 30 degree. Okay. So if I now run it, you can see that it will give out exactly the same thing. But please remember, this value should be in degrees here. It can't be in radians. So similar thing, you can do it in this is like rotation in Y, and like this is rotation about Z. Okay. And in a similar way, you can actually multiply rotation matrices, like similar to the Euler angles we had. So like if you want to multiply R1 times R2 times R3, you can do it like this. But please remember that the dimension should be consistent while multiplying matrices with other matrices or even vector. So the dimension should be consistent. Okay, you can always multiply a constant with a rotation matrix, like here we are doing. So A was a constant, A was actually 2. So this just does 2 times of this actually. You can see here. You can always multiply a matrix to a vector. So it is like rotating a point. So now A2 is being rotated by this this sequence of rotations. Okay. So in the course we looked at Euler angles. So here actually you can find out, so if you provide me the Euler angles, provide MATLAB the Euler angles, it can provide out the rotation matrix also. So here you can see that, okay, I want to rotate it by 30, then 45, then 60, this exact same thing as here. So then this is the function, and then you specify the Euler angles, so like here, but in radians you need to provide, so that's why this is present here. And then you do XYZ to mention what is the order of rotation. And if I now run it, you can see this is the one, and it actually exactly matches with this one. You can see the previous R. And if you want to go back to from a rotation matrix to the Euler angle, so like actually I am directly taking this rotation matrix and telling that, okay, I want the XYZ Euler angles. Now I am changing it back 2 degrees, so you can see, okay, it was 30, then 45, then 60. It works the same way. We also used one other one, which was if you provide the axis and the angle, you can find out the rotation matrix. That was slightly complicated with cosines and cosines. So here what you do is there are 4 arguments. So the first 3 are actually the vectors, so the x component of the axis vector, y component of the axis vector, z component of the axis vector, and the angle with which you are rotating. This should be in radian. Now this is the function, and if I now, so this is like I am rotating by pi by 6 along x axis, so y axis, so 0 1 0 is y axis. So you can see the output. So this is the output, and you can see exactly it is that. And similarly you can go from a rotation matrix to axis angle form. So if you want to know what is the axis and angle, so this is rot m2 axis angle, and then actually I am putting this one directly here. So you can see that, okay, 0 1 0, and this is actually pi by 6. So similar transformations are also present in case of quaternions and other techniques. So you can actually delve into much more detail, and you can search about it. Another important thing is like eigen values and eigen vectors. So you can actually directly find out the eigen values. So the function is like Eig, so like Eig, and then if I give R, let's say I want for A4, okay, what are the eigenvalues of the matrix A4? It will actually give out what are the eigenvalues. So you can see actually one of them is real and 2 of them are imaginary, so complex and then conjugate also. But if I want the eigenvectors also, so this is how you do it actually. So this V comma D, so actually you can have any other constants, any other variables here. I have chosen V and D, and you type it out. So actually it will give out what are the values. So you can see that, okay, these eigenvalues are stored in D and the eigenvectors are stored in V. So you can see that, and D actually it is stored in diagonal form. So you can see this is the first eigenvalue, this is the second eigenvalue, and this is the third eigenvalue. And actually we are trying to find out what is the eigenvalue for R2 actually, which was rotation about y by 45 degree. So you can see that we know that the eigenvalues are actually 1 and e to the power plus minus i5, and these are exactly that. And corresponding eigenvectors are like these. So actually this is one eigenvector, so this particular column. So you can see it is actually 0 1 0. So this is the k axis, so it matches with that. And the other 2 are actually complex, in complex form. So the eigenvectors are also complex. This was on eigenvectors and eigenvalue. So if you want to particularly, suppose I want the 1 2 element, what is the value of 1 2 element. So you can directly type like R in bracket 1 comma 2. So it will give you the 1 2 element of R. So if I now comment it and see, so you can see that 1 2. So this is the one we were inquiring, and it actually gives out. So suppose you also want to find out the column. Okay, so you want the second column. So this is how you do it. So this semicolon means that it will consider all the values which are possible actually. So it can be either 1 or 2 or 3. So it is actually doing like 1, 2, 3, all of them, and then comma 2. So here you can see that okay, it is taking the whole second column. So similarly you can do row wise. If you want to do the second row, you just do the opposite, and if I run it, you can see that okay, this is the second row it is considering. Again, this is just the norm. You can always find the norm of a vector. So like here actually if I do R, you can see that L2 norm of that particular one, it comes out to be 1. So this was it. Another one is sometimes you want to create a vector which is equally spaced. Okay, so this is one way to do it. So you do start with 0, then so this is like the starting variable, this is the ending variable, and how many points you want. So if I now run it, you can see that okay, this is 0, 1, 2, 3. So actually it will so what it is doing is it will create a vector from 0 to 10 which are equally spaced, and there will be 11 total points. So you can see there are actually 11 total points. So now if you want to do so suppose if you want to take every second element of that particular vector, how you can do it? You can so one quick way is like this. So you specify what is the start number, kind of number, what is the end number, and what will the spacing while you pick it. So it will actually start with 2 and it will go till the end, and it will skip every second one. So it will start with this one actually, then it will skip 2, then it will go to 3, and it will take 3, and so if I run it, you can see that okay, this is 1, then 3, then 5, then 7, then 9. Okay. So suppose you want to find out how many elements are inside a matrix or a vector. So one way is to use length. So length will tell you that okay, this was length of t, this was 11, so this is 11. And if you want the suppose the size, so like for a matrix the length will be different, so then you would be needing size actually. What is the size of the matrix, like what is min? So if I use size, it will actually give out okay, it was 1 by 11. So this is how you find out how many elements are there in a particular matrix. Okay, so this was about some basics of linear algebra, but there are always much more functions which are present. There are thousands and thousands of functions, so you can always look into them. So now we will see how to plot in MATLAB. So there are different techniques of plotting in MATLAB. So we will go over a few of them. Here I have introduced a new function. So this CLF. So what CLF does is it will clear the figure whenever I am running this file. Okay. So it is also one of the housekeeping function. So suppose I want to plot a circle. Okay. Now what I am doing is I will plot it in parametric form. So it will be like sine of t. So the x components will be sine of t, cosine of t, and the y components will be sine of t. So for that I am creating a vector t which starts from 0 and ends with 2 pi, and there are 1001 points inside it. I have chosen this one arbitrarily. Now what I am storing in x is cos of t, and in what I am storing in y is sine of t. So this t can, so the argument of cos or sine or anything, this can be actually both scalars or vectors. So if it is scalar, the output is also scalar, and if it is a vector, the output is also vector. Now this is the function. So plot x1 and comma y1. So it will plot. So this is actually x and this is y for the plot. Okay, and you can actually see it also gives help on how to do this. Then so this grid on, what it does is if I actually comment it out and if I run it, you can see there are no grids, and you can see that okay, this is the plot, actual plot here. So if I turn on the grid on, so you will see now that there is a grid present. axis equal, what it does is it will so the axes are equally spaced. So this this figure has the scaling in equal in both directions. So you can give it a title. So like here it is like trigonometric functions I am giving it. So like title, you can provide what is the label in this particular x and this particular y. So I am giving it x and y. And this function, what it does is it will actually specify what is the extent of this axis of this plot. So this is x minimum, then y x maximum, and then y minimum and y maximum. And if I actually remove this, comment it out, you can see that this plot becomes much more tighter. But if I want it much more spaced, and if I want my own ends, start and ends of these axes, I can always do this. So this was this. Suppose I now want to plot something over this plot. Okay, so here's what I'm doing now. So suppose I want to plot sine t over it. So again I'm taking this same variable t in x2, and in y I'm storing sine t. Now this hold on, what it does is it will hold the plot and plot over it. Okay, so if I don't have this hold on, so suppose I run, now I'm plotting x and 2. So if I now remove this one, means I'll comment this out, and if I run it, the previous plot will actually go away, you can see. But if I want to plot it over it, I'll just uncomment this and then again run it. You can see that okay, now this sine t is plotted over the previous one. Okay, so this was this. Now suppose I want to give legends to the axes. So you can see that okay, now the legends are also here. So this is how you means prescribe the legends. Okay, so this was one. Suppose now I want to do a 3D plot. Okay, so I'll actually comment these out for the time being. Now, so here what I'm doing is I'm taking an example. So here I'm plotting an helix. Okay, so the helix in parametric form, it will be like sine t, the x component, cos t, the y component, and t, the z component here. So this is this, and then if you want to plot, now I want to plot it in 3D, so that's why it is like plot 3, then x comma y comma z, and similar things. So now if I run this one, you will see this is now a helix. And in MATLAB you will have these particular functions on top. These will help you in determining different things. So like this you can actually use to rotate this figure. You can see I can rotate this figure. This one is for data points. So actually if I want to know, so okay, what is the value at this particular point, I can click here and it will give me the x, y, z values. And actually I can drag it and it will show the ones for different points. And similarly I can zoom it. So I can take this one and then drag, click here, it will actually zoom the figure. And similarly this one will zoom out the figure. Okay, and using this pan one, you can actually pan the graph, and if you double click it, it will go to the previous one. Okay, and suppose now what I want to do is I want to highlight every 50th point on this particular line, on this particular helix. Okay, so but I want to just plot the points. I don't want a straight line. So in plot it does is it will take each of the points and it will join them by straight lines. So but suppose I don't want to join these ones, so I want to just highlight every 50th point. So then what I do is I'll use scatter plot. So this is scatter 3. Then I'm doing a very similar thing what I did previously also. So like in x I'm starting with 1, I'm going till the end, but I'm only taking every 50th point. And similarly for y and similarly for z. If I now run it, you will see that now okay, these are now circles. here. Suppose I want them as x's. So like I can give a comma and provide that okay, this should be like in x, like cross. Okay, so you can see now if each of them are like crosses. Suppose I want them in red. Okay, so I can write R and then do it, and you can see now they are in red. So there are different techniques on, you can change their color, you can thicken the lines, you can do all sorts of things here. So you can go to the help files of these particular functions and you can see what other properties you can change. Okay. Now finally coming to a quick one. So suppose you want to just plot a function. So suppose I have a function x square plus 2 y square minus equals to 1 actually. So this is like an ellipse. I want to plot an ellipse. So this f implicit, what it does is it can plot functions like, okay, here I am specifying this is a function in x and y, and this is the function. So actually you should specify it will be like f of x comma y equals to 0. So this is how it's specified. And if I actually run it, you can see that it is now an ellipse. You can see. So the semi-minor, semi-major axes are ones for ellipse. You can see that this is x squared. So the semi-major axis is actually 1. Here it will be like square root of square root of 2. So it will be like that. So this was on how you plot in MATLAB. So there are many different other techniques on plotting. We are highly encouraging you to look into those all as well. So now we will see how to use loops in MATLAB. So loops will be very much helpful in this particular course. So loops, so there are different functions which can be used in loop, like for, if, while. Here we will see a few of them. So suppose we are given a problem like this. So we need to collect all the numbers which are in between 0 and 50, including 0 and 50, which are not divisible by 5, and we need to separate them into two groups. So first one which will contain which are divisible by 3 or 7, and the other group will contain the remaining numbers. Okay, so we'll start like this. So this is actually another way of specifying a vector. So here this is the starting variable, this is the ending variable. They are separated with commas, colons, and in between you specify what is the step size you want. So if I now run it, you can see that okay, this is the output. So this was the so actually this t is the vector, you can see. Okay, so it starts from 0 till 50, and I have specified the step size as 1, so it actually goes like 1 2 3 4 like this. Okay, now here what we are doing is we are making these two groups separately. So the first one is like x and the second one is y. We start with null. Okay, so this, if you don't have anything in the brackets, actually this is like null. Okay, then what we are doing is, okay, we are starting a loop. So here you can see we are starting that for. So for this loop will run, the looping variable is I, so it will run for I. It will start from 1, so this is 1, and then length of t, so it actually goes to length, so that's why I am using length of t. So they like, this is the starting variable, this is the ending variable, and this is the step length it will take for in the loop. So it will start with 1, execute this loop, add 1, execute this loop, and it will go till I is equals to the length of this particular vector t, which is 51 actually here. Okay, so now what I am doing is I am using C. So I'm using the ith variable, taking the ith variable from this t. So one thing to mention is in MATLAB the variables are stored like 1, 2, 3, 4. So in other places like in C, the first variable is actually the position is actually 0, but in MATLAB it starts with 1, so you need to be careful about that. So I am also starting with 1, so that's why I am using T. So I am storing each of them. So like I am taking the first element now, so I is 1, so T of 1, so it will take 0. Now this loop will start. Okay, so this is an if loop. So what we'll check is, so this mod what it does is it will try to find out what is the remainder, like what is the remainder of that. So this is the first value, and what you need to divide it by. So I'm dividing C divided by 5, and this tilde and then equals to, this means not equals to. So it is checking if the number when divisible by 5, what is the remainder, and then that if that remainder is not equals to 0. So actually what we are doing is we are checking that if it is divisible by 5 or not divisible by 5. So if it is divisible by 5, then the remainder will be 0, and if it is not divisible by 5, the remainder won't be 0. So that's why we are considering those particular values which are not divisible by 5. So it will come into this. Now I want to separate into ones which are divisible by 3 and then divisible by 7. So similarly I am using mod, then C comma 3 which are divisible by 3. Then what this one does is like this is like the new x will be old x and then concatenated with this particular value C. So it will always store to the right of x. So it is like divisible if it is divisible by 3, then if it is else if it is divisible by 7, then it will store C. So then else I am ending with else it will be stored in y. So that's how we were given in this function. And then each of the loop actually needs to end, means complete with an end. So this if loop, this if, else, then this end. So this if should have this end, and then for this loop, for there is this end. And now if I run this, you can see, okay, this is the values which are stored in x. So these are which are not divisible by 5 but divisible by 3 or divisible by 7. So you can see that all these values satisfy these things. And these ones are ones which are not divisible by 3 or 7 or 5. You can see these values satisfy this. So this was a quick example on how to use loops in MATLAB. There are other different types of loops also present, like while, else, to while, and various other ones are present. You can also look into them. In this example, we will see how to solve linear equations. So we can always have linear equations which we can separate into the form like Ax equals to b, like where a will be, so if we are given some n equations and m variables, so this a will be like n by m, x will be a m by 1 vector, and similarly b will be a m by 1 vector. Okay, so here I have taken one example. So suppose we are given an equation which is like x minus 2y equals to minus 2, and second equation is 7x minus 3y equals to 19. So suppose I want to solve for the values of x and y. So we can separate it in the form like a and then b. So a will be similarly, so this is 1, then minus 2, and then 7, and then minus 3. So this is in matrix form. And similarly b will be minus 2 and then 19 in a column form. Okay, so now you can solve for it. So there are different ways to do it, so I have taken two of them. So this is one of the ways. So you take that, okay, this is the function, so link solve, and then you provide the a and b matrices, and if you run it, you can see that, okay, the value of x here means the first variable is 4 and the second variable is 3. That solves this particular two equations. Another way is you can do this kind of thing. So a, but in the reverse slash. then b. Okay, and if I run it, you can see that these two give the same value. So this was on how to solve linear equations. Now we will see how to do symbolic algebra and symbolic other manipulations in MATLAB. So in MATLAB, the symbolic manipulation, the symbolic toolbox is not as great as the ones in Maple, but it can do most of the work. So if any of the variables you are working with is symbolic, so you need to specify that they are symbolic. So this is how you do it. You write SYMS and then you write out all the variables, spacing, giving a space in between one of each one. Okay, so now suppose I want to find out what is the angular velocity, angular velocity of XYZ Euler rotation. So here actually I have written out what is the rotation matrix about x. So here I am rotating x about x by a, then about y by b, and then about z by c. So the rotation matrices are like this. Actually, if I run it, you can see. I will comment out the outputs. You can see, okay, r of x is like this: 1 0 0, and 0 cos a minus sin a, 0 sin a cos a. So you can see these are in variable forms. So these are not giving out some particular values. Okay. So now suppose I want to multiply them. So that's what I have done here. So this is the combined rotation matrix. Okay. I'll just use this. So you can see this is the combined rotation matrix. So now if I want to find out what is r dot, we can't directly actually differentiate with respect to time. So what we do is we will do it sequentially. So r is like rx times ry times rz. So if I do r dot, so the first term will be d of rx divided by dA times dA by dt times rx times ry. Second term will be like rx times d of ry divided by dB times dB by dt times rz, and so on. So that is explicitly what I have done here. So you can see this is differentiating. I am differentiating. So diff means differentiating. So this rx with respect to a, then times ry times rz, because so this dA is like I'm shorting it for dA by dt. So but this is a scalar, so I can just put it at the end. Similarly, this is I'm differentiating ry, and then I'm differentiating rz. So now if I run it, so the r dot actually looks something like this. It is huge and complicated in nature. So similarly, I can find out what is that omega r. Okay, so omega r is like r dot r transpose, and if I want to see what is the output of this, so this is r omega r. You can see this is actually a skew symmetric matrix also. So the diagonals are 0 and the off diagonal terms are means kind of negative of each other here. So this is omega r, and now this was the capital omega matrix, and now if I want the vector, I'll just choose what are the elements. So actually this is actually x, this one is particularly y 1, 3, and this one is actually z. So now if I run it, you can see that okay, this is the omega in vector form. Okay, and now this was actually the space fixed angular velocity. Suppose I want to find out what is the body fixed angular velocity. I can always do like r transpose r dot, but I can also like I already have what is omega s, but the space fixed angular velocity. I can multiply r transpose with s and get back what is omega b. And if I now do it, and what this simplify does is it will actually simplify some of the equations. It can be too long, means like some of the terms will be like sin square theta plus cos square theta, but it will simplify all those terms. So this is omega b in, which is like the body fixed angular velocity. Okay. So this was like finding out omega. Another one is suppose in controls you want to find out what is the exponential of a matrix. So suppose I am given this matrix as A and I want to find what is exponential of at, e to the power at. So this is how you specify it, expm and then a times t, and t is actually declared here as you can see as a variable, as a symbolic variable, and you can see that it will give out what is the value of e to the power at. So this will actually be useful when you are doing controls. Okay, and similarly you can do Laplace or inverse Laplace here. So I have defined, so something like you will later on see that okay, I want to do so si minus a, the whole inverse, and I want to take the Laplace inverse of it. So this is what I am doing. So s, then I means this is the 3 by 3 identity matrix, minus a, then to the power 1. So this is the k matrix, and I want to do the inverse Laplace of this. So you can see that if I now run it, so this is this. So this is actually giving out the e to the power at in inverse Laplace form. So if I actually compare both of them, so both of them are exactly the same, as you can see. So this was a few of the examples, and you can see if I do means like e1 minus e2 here, you can see that this is 0 0. So they are exactly same. So this was a few examples on how to use MATLAB, how to use the symbolic package in MATLAB. Right? Now we will see how to write a function in MATLAB. So functions are very much useful if you want to do some repetitive work. So suppose you have a particular function which spits out the value, but you want some thousands values for that. So it's better you define that function and you just call that function every time you want it. Okay, so here we will, I'm giving an example of the Rodriguez rotation formula. So suppose I want a function which will give out the rotation matrix if I provide the axis and the angle of rotation. So here I am doing it in symbolic form. Okay, so k I am specifying as suppose x-axis. So this is 1 0 0 and the angle of rotation is phi. So this is how I will define the function. So the functions can be defined in two ways. Either it can be defined in the same file, or it can be defined as a separate file. So as a separate file, if it is defined, so then what happens is any other file in that particular directory can also call up that function. But if you want it in a single file, you can always do that. So suppose you will define it in a single file. So what you do is you will put that function at the end of the whole script. So it should always be at the end of the script. So always there can be multiple functions at the end of the script, but there should not be a single line that is executable after this. Okay, so the syntax of function is you will write it as function, then what is the output of the function, then equals to, then what is the name of the function, and then the arguments of the function you want, what are the inputs to the function. So please be aware that this function should not interfere, means like clash with other functions which are predefined in MATLAB. So they should have a unique name, and it the function should always means stop with an end, so that it knows that what is the end of the function. So here what I'll be using is the matrix form of the Rodriguez rotation formula. So it actually looks something like this. So the rotation matrix R is equals to identity plus sine of theta times k. So I'll come back to what is k, plus 1 minus cos theta times k square. So this k is a matrix, is a skew symmetric matrix made up by the elements of the unit, means normalized axis of rotation. Means you normalize the vector which is the axis of rotation and you form the skew symmetric matrix from it. So that is exactly K, and it is actually same as the one which is taught in the class, but the one taught in the class is in the vector form. Here it is in the matrix form. Okay. So so what I have done is I have defined a separate function called skew, which will take the vector as an input and it will give out the skew symmetric matrix as output. So you can see that okay, I am taking K, but then so the first element is 0, then the minus Z component, then Y component, then Z component, and so on. So this will give out the the skew symmetric matrix here. So I am defining that capital K is that particular one. So I am calling this function here. And now I am telling that okay, the rotation matrix is identity matrix. So this 3 by 3 identity matrix plus K times sin phi plus K square times 1 minus cos phi. So this is that. And now in the main body you can see that okay, suppose I want to find the XYZ Euler rotation about so first by x by A, then by y axis about y axis by B, and then about z axis by C. So I am calling that function. So I am specifying what is the vector. So this is a K. So this is this K. So this is 1 0 0, then A comma A, then similarly Y comma B, then Z comma C. And if I now see the output, so this is actually that particular matrix, the rotation matrix, which will be specified by this values. Okay. So this is how you define a function. So this can be something else also, like you can define a function. So later on you will see that when we solve the equations of motion, you need to define the state space form of the equation of motion as a function. So this is a quick glimpse on how to write a function. We will actually see much more examples of function later on in this video. Now we will see how to solve a particular function. Okay, so means this particular function can be anything, means like it can be polynomial, it can be transcendental, or anything in nature. So we will again start with CL, means clear means the housekeeping functions. So now I am defining the function here. So you can see this is another way of defining a function. So this at means you are defining a function. This is the input variable, this is the function name, and then what you are doing is then you are doing x cube minus 6x square plus 11x minus 6. So this dot to the power 3, what it does, it will actually do element wise multiplication. So actually if x is a scalar, it will just do scalar thing, but if x is a vector, then it will do element wise multiplication. So it means like if I will pass this t vector in this function, it will actually do t cube, but it will do it in, means element wise it will cube it and then spit out the value. So I am defining the function f1 here, and so the way to do it is so there's a function called fsolve. So fsolve, then you specify what is the function, and here you need to provide an initial guess. So this function, as you can see, this is the cubic polynomial. So actually there should be 3 roots of the equation. So I am actually solving f of x equals to 0. So there should be 3 values. But what this particular function fsolve does is it will try to find the nearest, means you need to provide an initial condition, and it will find the nearest value to it. So it actually uses some kind of gradient descent method to find out the solution. So this is how you do it. So actually I am providing an initial condition x0 as 0. So this is the initial condition, and if I now run it, you can see that okay, 1 is actually one of the solution for this particular equation, and actually I have also plotted the equation. You can see here, you can see that okay, 1 was one of the solution, but you can see 2 and 3 are also one of other solutions. So actually I have given 0 as the initial condition, so the nearest one is 1. So suppose if I give 4 as an initial condition here now and run the file again, you can see now the output is 3. So it actually finds out the nearest one to 4, this is 3. And similarly, suppose if I give 2.1 as one of the solution, you can see that okay, the output is 2. So fsolve actually gives out only one solution. It will give out only one solution which will be close by to the initial condition you provide, initial guess you provide. So it's also important that you provide a good initial guess, because if the initial guess is too far from the function and the function is too complicated in nature, fsolve can't find out the value. So this was how to solve a function, a general function. It means it need not be a polynomial. It can have tan, log, sine, cosine, exponentials, everything, but it can solve it. Okay. Now we will see how to solve differential equations, means linear differential equations in MATLAB. Okay. So here actually we will be solving the differential equation of a spring mass damper system. So the equation of motion is something like mx double dot plus cx dot plus kx equals to F, where F is the force applied on the spring. So the spring and mass, spring and damper are actually added in parallel to each other. So here actually I am defining another thing here. So global. So global, what it does is it will define, you can define some of the variables which are global, and in the function. So suppose you can have multiple functions where you will call them, but some of the variables there are will have the same values, will have a global value. So you can specify that okay, these are the global functions, and you can always save these values and use it in the other function, but also in that function you need to specify which of the function variables are global in nature. So from the main file it will pull out the value if it is in the workspace, and it will provide it inside it. Okay. So here you need to provide the equations in state space form. Okay. So the differential equation is something like this. So mx double dot plus cx dot plus kx equals to F. So what we will do is we will take that okay, we will have two variables, which is like x1 is x and then x2 is x dot. So we will now write the differential equation in terms of x1 and x2. So similarly, so x1 dot is as x dot, which is x2, and then x2 dot is like this term. So we will take all the terms to the left, so it will be like f minus c x2 minus k x1, so divided by m. So like this is the state space form of this particular second order differential equation. So if you have an nth order differential equation, so there will be n first order differential equation. As you can see, all these terms are first order differential equations. All right. So in this function we are defining that explicitly. Okay. So this is the output of the system. So like output here is the x double dot term. Okay. So I am taking f1, which is like x2, and then f2, which is f minus cx2 minus kx1 divided by m, and then I am clubbing them together, which is the output of the function. And input of the function is like t comma x. So t is actually time. So some of the variables can be dependent on time. Here there is no explicit dependence on time for any of them. So then x. So x is the input variable, and this is how you specify it. You specify what is the time you are going to simulate these equations. Okay. So I am doing from 0 to 10 with a step of 0.1. You need to provide some initial conditions always to solve a differential equation. So I am giving that okay, x1 at t equals to 0 is 1 and x2 at t equals to 0 is 1. So actually x is 1 and x dot is 1 at time t equals to 0, and this is how you will solve it. So you solve it by ODE 45. Then for the first argument is you call in the equation of motion. So this is like the equation of motion, or any it means like not even equation of motion, you call the differential equations, the state space form of the differential equation. Then you provide what is the time you want to solve for it and the initial condition for this one. So this t comma y will actually give out the time and the y vector. Y is the output vector here. Okay, and if now if I run it and if you see what is y, so y will be in two forms. So this left column is all the values for means x, and the right one is all the values for x dot, and these are corresponding to t. So if you have t, so if I plot t comma y, actually this is the plot you can see. So this is how it behaves. So this is x1 and the red one is x2. So if suppose I change the initial condition and run it again, you can see that the dynamics of the system has changed also. So this is how you solve the differential equation. You can have multiple differential equations also. Okay, so ODE 45 can solve almost most of them. There are also other differential equation solver like ODE 23s, ODE 15s, ODE 15 and so on. You can look into them. So, but in most cases ODE 45 is well enough to solve differential equations. Now we will see how to solve optimization problems in MATLAB. So optimization problems, it can be either maximizing or minimizing function, but in MATLAB, so we are using fmincon. So this fmincon function actually can only minimize the function. So suppose we are given a function, means optimization function like this, so that we need to maximize x1 square plus x2 square, but subject to this constraint that x1 square plus x2 square equals to 1. So this constraint need not be of the same form as the optimization function, but here we are choosing this way. So what we are trying to do is, in a circle of radius 1, we are trying to find the x and y coordinates such that x square plus y square is maximum. So this is the actual problem statement here. So here we will need to define an optimization function. So this is the optimization function. So it's like x1 square plus x2 square, but there's a minus. So because we are converting it to a minimization problem here. Then so fmincon is the function here. So fmincon actually has a lot of inputs. I'll show you. As you can see here, so the first argument is the function itself. So here this is the optifun function. Then x0 is the initial conditions you are providing. So in here also you need to provide some initial condition to solve the optimization problem. Here we are choosing it to be 0, 0. Then a and then b. So these are, if you have the constraint equations which are linear in form, so then you can separate them as ax equals to b. So a and b are those matrices. So a and b are the inequality constraint matrices. AEQ, BEQ are the equality constraint matrices. LB and UB are, you can provide upper bounds and lower bounds to the optimization variables. And non-L cone, so this is like the if you have the optimization constraints which are non-linear in nature. So here we have non-linear equations. So we are defining this as a constraint, means like this as a function as called C1st. Here this is C and CEQ, the outputs. So C are the inequality constraint and CEQ are the equality constraint. So we have defined that one. So x square plus y square minus 1 is equals to 0. There are no inequality constraints, so this is kept blank, that's why. and so these are the inequality constraints. So this is there. So now if I actually run this, you can see, okay, this is the solution. So this is exactly 1 by root 2 and 1 by root 2, and you can see fval will give you the value of the function, optimized function. So this is -1. So because we have converted it to a minimization problem, that's why this is -1. And you can exactly see that, okay, yeah, in a circle, if we are trying to find out where x square plus y square is maximum, it is exactly at y equals to x. So that's why it is 1 by square root of 2, 1 by square root of 2, and the value is 1. So this was how you solve optimization problems in MATLAB. Now we will see a few basics of control systems. So a few of them are like, suppose you are given a state space form of a system, you want to convert it to the transfer function form. So suppose I am given the A matrix, B matrix and C matrix as this, and run it and show you. So like A is this, B is this, C is this, and D is 0. So suppose I want to find out what is the state space, the transfer function form of this. So that you do it by this function. So SS to TF, then you specify what are the A, B, C, D matrices, and the outputs are the numerator and denominator polynomials of that particular transfer function. So if I actually see what is num1, so this is actually 0 1 0 0, so it will be like s cube, s square, s, then 1. So this is on top, this is s square, and if I see what is then 1, so this is that. So this is x cube plus 6s square plus 5s plus 1. So these are the numerator and denominator of the transfer function, like the coefficients of the polynomial, right? So, and so sometimes you need to means when you will do root locus or Bode plot, you need to define these matrices as systems, right? So to define it as systems, if they are in state space form, is you do SS and then you provide what are the A, B, C and D matrix. And if I just now show you, I'll just comment this and run it again. So you can see that, okay, this is sys1, I have defined this one, sys1. So this is A. You can see also they have mentioned what are the state space variable x1, x2, x3. This is B, this is C and D, and it has determined, okay, this is a continuous time space, continuous time state space model. Okay, so this was given a state space model. So but if you are given an transfer function, so you can do it like this way. So 0 1 0. So I'm taking actually the same result from here. This is the denominator, and you tell them what is the numerator and denominator. You do TF to SS, and the outputs are A2, B2, C2, D2. These are the output polynomial ones. So if I now run it, you will see that, okay, this is A2, this is B2, this is C2, then this is D2, and it is exactly the same as this one, the previous one. Okay, but just it's in actually the variables are rearranged, but you can see the numbers are same here. Okay, so this is, if you are given a if you are given a transfer function form, you are now coming back to state space form. So sometimes you need to have the Jordan form of a matrix. Okay, so suppose I was given this A1 matrix, but I want the Jordan form of it, and I want the vector also, the eigenvectors of that. So this is the Jordan form. So this is diagonal form, and this is the P matrix which we have seen. Okay, so you can use this P matrix and V, and you can use something similar to the similarity transform, and you can convert A1 into different state you means like converting the states, you can have a different state matrices. Okay, suppose another important thing is you want to find out what is the exponential of a. Sometimes you need to compute what is e to the power at, right? So then what you do is you will do sims t, and then this is the way to get exponential of a matrix expm. Then you do a2. So I'm choosing a2 times t. Now if I run it, so you can see EAT I've defined the variable. So this is the one. You can see this is long in nature, but it can compute the exponential of a matrix. Okay, so sometimes what you want is, suppose you have a system. Okay, either it be in a state space form or in transfer function form, but you want to know what are the zeros, poles and gain. Okay, means like if it is even in transfer function form, it can be in polynomial form. So what you want it in k times, so s minus a1, s minus a2 divided by s minus b1, s minus b2 and so on. So this is how you do it. So the outputs are z, p and k, and you do zpk data, then you provide what are the systems. Okay, so now if I run it, so actually I have given this as sys2. So sys2 was this polynomial one. So you can see that, okay, this is the one. So actually if you open z now, so if I open z, so you can see these are the zeros, 0, 0. And if I see the poles, so the poles are these are the poles. So minus 5.04, 0489 and so on. These are the 3 poles. And what is k? I can also see k. So k is actually 1. K equals to 1. So this is how I can also find out the poles and zeros and gain of a given system, if it can't be done easily. So suppose now we want to see the evolution of the system given the initial condition. Okay, I want to see what is the output of the system. So what you do then is you provide the time you want to simulate. So I'm giving it starting from 0 till 25 seconds, and this is the step time. I need to give some initial condition. So this is 1 0 0. I'm giving this as initial condition. I'm using the system 1, which was the state space form of that one, right? So actually you can see that C001. So actually x3 is equals to y, but I am giving only initial condition to x1, others are 0. Okay, you provide the initial condition and you give the time, and it will simulate it, and this is how it looks. So it actually starts from 0, and this is how it behaves. Okay, so let's say you want to see the step response of a system. So how you do it is you type STAP and then you type the system, and if you run it, you will see that, okay, this is the step response of the system 2. Okay, and suppose if you want the impulse response, so you do impulse, then similarly the system, and if you run it, so you will see that, okay, this is the impulse response of the system. Okay, and similarly if you want to do Laplace or inverse Laplace transform, so suppose I want to know what is the Laplace transform or inverse Laplace transform. So for that, suppose I'm trying to find out what is the Laplace transform of e to the power minus at. Okay, so I'm telling that f is equals to e to the power minus at, and then this Laplace f will give me the Laplace transform of this particular function taking t as time. Okay, so it gives out that 1 by a plus s is the Laplace transform of this. But okay, again if I want to get the inverse Laplace transform, I use I Laplace, and then suppose I want to get the inverse Laplace of this particular one exactly. If I do it, you will see that, okay, I is e to the power minus at, which is exactly which we started from. So this is how you find Laplace and inverse Laplace transforms You can use these ones also to find out that inverse Laplace of s minus s times I minus a, all those things, minus bk, all those things. You can use these functions. So now we will see how to plot root locus in MATLAB. Suppose we are given a system with these polynomials. So this is the numerator coefficients of the numerator polynomial, and these are the coefficients of the denominator polynomial, and we are defining it as a system, as a control systems. Okay, then you will do R locus and then the system, and it will actually give out the root locus. And if I now plot it, you will see that okay, this is the root locus of the system. So it actually originates starting from the open loop poles, and it goes to the open loop zeros, or it will go to infinity as the gain increases. If I now turn on the grid, you will see that okay, these you will see that it's kind of a polar plot, and actually if I do axis equal, you will see that it's exactly like a polar plot. So these circles are the gain lines, so they correspond to a particular gain value, and the straight lines originating from the 0, 0 points are the zeta values. So this is like 0.22, this is 0.6, and you can also use this data tip thing, and you can see a particular point here. So you can see that okay, this is 0.84. You can see that yeah, this is dampened, the exact one, and you can see that okay, the k value is here 3. So but like the gain, the k value, the gain value is 1.88 here, and similarly this is the pole of this particular point, means what is the value of the real part and imaginary part of it. You can see the frequency, you can see the overshoot value, and all other details in this particular one. And you can choose different points also. So this is on the real line, and you can see that the pole is at this particular point. Okay, so this is how you do it using transfer function. You can also do it using state space form. So suppose I am given a state space form like A, B, C, D matrices are given. I choose that okay, this is the I'm defining this as the like the control system, and I can also plot this one, and now you can see that okay, this is the root locus of the system. So there are 1, 2, 3 3 poles, and it all of them goes to 0. There are no zeros in the system. So suppose now I want to kind of animate a plot. I will show you how to animate a plot in MATLAB. I want to show that okay, as the k increases, the pole starts from 0 and it goes to infinity in this particular plot. Okay, so what I am doing is this r comma k, what it does is it will extract what are the roots and what are the gains. So there are 3 branches, so it will actually accumulate 3 r's, and it will also get the corresponding gain values. So I am doing exactly that. I am taking the first root, the real part, then the imaginary part, plotting it in I am doing a scatter plot, so in blue star, and similarly for the second root and similarly for the third root, and I am also writing out what is the value of k here. I am pausing the plot for a while and then I am clearing it and again plotting it. You can see that I am using a for loop here, and now if I run it, you will see that okay, this is how the poles will start to move as k increases. You can see it started from the zeros and now it is going towards infinity as the gain increases. You can see that it goes to infinity. So this was like how to get animated plots in MATLAB, and also like how to plot root locuses if you are given a system. It can be either in state space form or even in transfer function form. So either in time domain or in frequency domain, you can plot them both. Now we will see how to plot Bode plots in MATLAB. So like previous times, you can define the system both in state space form or in like the transfer function form. So both in time domain or in frequency domain. So suppose I am given means the numerator transfer polynomial coefficients are like this, and if I do Bode plot and then I give this one, it will actually generate the Bode plot of the system. You can see, okay, this is the Bode plot of the system. So this is the magnitude plot and this is the phase plot. And similarly, I can do it in like the state space form. So I provide A, B, C, D matrices, and I declare it as a control system, and then I do Bode plot. And this time I'm also turning on the grid so that you can see, okay, this is how the system looks like. Okay, and you can see the grid on here, and you can see that this is actually indeed like a logarithmic plot in this one. Okay, another thing you can do it in here is you can find out what is the margins of the system, what is the gain margin and phase margin. So what you do is you just type margin then the system. Okay, and here if it runs, you can see that, okay, if I am seeing for the system 2, okay, this is the gain margin. The gain margin is actually 20 dB and the phase margin is actually 180 degrees. So it can directly find out what is the gain margin and phase margin of the system if you give the system to it, right? So this was how you get Bode plots using MATLAB. Now we will see how to check the controllability or observability of a given system. So if we are given a system, we want to check if the system is controllable or observable, or means like get the observability and controllability matrices. So suppose we are given the matrices as A, B, C like this, and so you do CTRB, then A comma B if you give it, so this will compute the controllability matrix. And then what we are doing is we are trying to find out what is the rank of controllability matrix. And similarly OBSV, and then if you give it A comma C, it will actually calculate the observability matrix. And again we are calculating the rank of the observability matrix. So if we see it, so this is the controllability matrix, you can see, and the rank is 3. So the system here is controllable, and this is the observability matrix, and you can see that the system is observable. Again, now if I see the observability matrix and controllability matrix again for another system, so you can see that, okay, I'll actually comment these things out. Okay, so this is the controllability matrix. You can see the rank is 3. This is the observability matrix, but you can see the rank is actually 2. So this system is now controllable, but this is not observable, right? And again, this is another example. So you can see this here, the Q is, this is the Q, so this is a 2 by 2 matrix, but the rank is 1. So the system is not controllable, and you can see that here the observability matrix is 2 by 2 and the rank of the observability matrix is 2. So here the system is actually observable but not controllable. So this was how to check if the system is observable or controllable and controllable by generating the observability or controllability matrices and checking the rank of the matrices. So suppose you want to use state space method and use the pole placement method to place the particular poles in your desired choice. Okay, so suppose you are given a system. So here actually we are using a different type of representation. So this is a Zpk representation. So here what you do is you provide the zeros and the poles and the gain of the system. So So suppose the zeros are at these locations, the poles are at these locations, and the gain value is 1. Okay, so this is how then we define the system. So Zpk, so this is our control system. So actually, if I show you what is this, you can see that okay, this is the transfer function, and you can see that the zeros and poles and the gains matches with the system. Okay, so now we are converting it into the numerator and denominator polynomial as required. So we are getting the numerator and denominator polynomial, and then we are converting it to the state space model. Okay, so here we are starting from the zero pole, we are given the zeros, poles and gains, then we are converting it into a normal polynomial form of the transfer function, and then we are converting it to ABCD matrix. And then what you do is you this K matrix, you want to find out what is K, and remember here what you are doing is, so U is equals to minus Kx, so you want to find what is K. So you give the A and B matrices, so A is a matrix, B is a vector, and what you do is you write where do you want the poles to be. So suppose I want the poles to be exactly at 4.5, minus 1.5 and 1. So I give that and press C. So let's see. So it gives me okay, these are the values of K, specified K. And so suppose I previously want to find out what was the eigenvalue of A. So you can see the eigenvalues were this. So now after pole placement, you will see that okay, if I want to find out what are the eigenvalues of A minus Bk, now it will be, so you can see that okay, these are the positions and these are exactly the ones I needed, and K are the gains of that K matrix. So this is how you do pole placement using MATLAB. So you use this particular function place, and you provide A, B and the required location of the desired poles. Now we will see how to use Simulink in MATLAB. So Simulink is a part of MATLAB which is a graphical interface which you can use to solve different problems, mostly in controls domain. So to start Simulink, you can see there's a button here for Simulink. If you press it, so this kind of a pop-up window will open up. So we'll start with the create model. I press that. So this is how the Simulink interface looks like. So you will have a blank canvas where you will work on. I'll come to this later. You will have a library browser here. So we'll use different blocks and other functions. So these will be found in this library browser. So if I click open the library browser, you can see it actually looks like this. So there are different kinds of blocks available, thousands and thousands of types. You can explore these. Okay, but you can actually directly start using Simulink directly from its blank canvas. So suppose I want to get the step response of a system. If I am given a transfer function, I want to find out what is the step response of a system. Okay, so suppose for that I will need a step block. So actually if I start typing out, so you can see that it actually comes out. So actually what you will do is you double click on the blank space and you start typing. So this is a step, so I'll click this. So this is a step function. I can also get an output of the system. So for the output of the system, I'll actually get a scope. So it's called a scope. Okay, so this is a scope. And actually suppose I want to just see first the output of the system for a step response. Just the step response out, means like how it looks. So actually you can see that there's a arrow here and arrow here. So I need to join these two, and this is how it will look. Okay, and actually if you open this block, you will see there are different types of things. So step time. So step time is actually at what time the step response, means step ladder starts. So at what time the value becomes 1. So actually here the final value is 1. You can change the value also. It can have a different initial value also. Okay, and this is the scope. So if I open it, double click it, you will see that it's kind of a plot. Okay, and here at the top you can see that this is the stop time. So it will start with 0 and this is the stop time, and if you press this run button here, it will simulate the model, and you can see that it is running on the background. And this is the step response. So actually the step response actually starts from at 1 second. Okay, so you can actually change that also. So this step time, if I go make it 0, and so actually you will have a run button here also. I can run it from here also directly. So you can see that it starts from 0 itself and it starts at 1. So suppose I want to have a transfer function. So actually you can get a transfer function block. So you can see this one. So I can edit it now. So suppose I want it to look like this. So in transfer function you give out the coefficients of the numerator and denominator polynomial. So you can actually increase the size of it also. So it looks like 1 by s into s square. So and actually you can drag to the middle and it will kind of make it. So actually I can delete this line and I can connect this to this and then this to this. So it's like open loop transfer function. So what is the open loop thing? So you can see that it's like a ramp input. It goes on till infinity. So suppose I want to see what is the closed loop response to a transfer function, to a step response. So for that I need a summation block. So if I type sum, you will get a summation block. So it will look like this, but actually if you see closely, I can zoom it. So just scrolling zooms the thing. So both of them are plus, but I need one of them minus. So I'll change the last one to minus, and you can see this is minus now. Now I can actually, if I drop it in between, it will actually not do anything. So I'll just delete it. Delete the line, connect this to this, this to this, and I connect the output to this. And if I now see the scope, so this is the response of the system. You can see it is much different than the normal one. So suppose I want to see the output, two of them. So one will be like the direct output and one will be the closed loop output. Means like one will be the open loop one and one will be the closed loop one. So actually in the same scope. So what you can do is I'll do this, press this configuration button. So there only the number of port is 1. I can change it to 2, and I can change the layout of the grid. So actually I made it 2 by 1. So something like this. Okay? And if I press OK, and you can see now there are two outputs, means two inputs to this scope. Now what I can do is, if I use the middle click button, I can grab it and move it. I'll make a copy of the system. So for making the copy, I hold control and drag one of the system, and it makes a copy of the system of the thing, whichever thing you have selected actually. And if I now run it, you can see the top one is the open loop one and the bottom one is the closed loop one. So now let's add a controller in between. Okay, so the controller, you can add it as a transfer function itself, and there are also PID controllers here. So actually I'll directly use the PID one. So if I have a PID controller here, you'll see this is the PID controller. So there are different kinds of block, I should mention that. So this is like a, so it has an input and an output, but like this for the step response, you can see here it only has a out port, okay, and the scope one, it only has input ports. So these are called sinks and these are called sources, okay. So this was just a quick thing. So suppose I also want to control the system. I'll make a copy of the system, the whole thing. Okay. And I'll increase the port to 3 now. I want to see all of them at once. I can increase the size of it. Okay, I'll connect this directly to here, this to here, this to here. And it is very intuitive to use Simulink because it's just creating lines and things like creating circuits. Okay, so if I open this PID controller, so right now the proportional gain is 1, integral gain is 1, derivative gain is 0. So actually the controller looks something like this. It's not the normal one. It's not like Kp times Ki by S plus Kd times S. It looks something like this, so that the controller is like causal. Okay, so let's stick with these values and see what is the output of the system. Okay. Okay, you can see that, okay, now the system has started oscillating. So suppose then I'll add a little bit of damping. So just say suppose 1. You can see that, okay, now it is starting to oscillate, means like it is damping. Actually I can increase the time here. So suppose let's say till 20 seconds I want to see what is the output. You can see it is starting to, but this MATLAB PID thing has a tuner inbuilt. So there actually you can tune these parameters. So you can see this tune button here. So if I press this button, it will automatically linearize the plants. And the tuner thing will open up automatically. Okay, now it is giving us one of the tuned values, but actually you can tweak with the system. So suppose you want it to be a little bit faster. Okay, so this is how it will look like now. It maybe you want it little bit robust. So this is how it will look like, but you want more aggressive. This is how it will look like. So it will increase, means like it is aggressive, so the peak overshoot increases. So just let's reset the design to its original values. Okay, and you can have this update block thing, right? You can press this and it will apply all the PID values it has generated to the normal PID block here. You can see that. If I press OK, now if I run it, you will see the system is, means the peak overshoot is not that high now, and it actually reaches 1 very quickly. But yeah, means there is some transient response here. You can actually tweak it more to your liking, but this is a quick way to do it. Actually the system was much more stable initially, that's why it is it settles much quickly. But suppose if I change the system, suppose the system now looks like this. Okay, this you can see, okay, this is the response of the system. This is the open loop response, this is the closed loop response. And now I can again open the PID block. I can tune the system. Okay, you can see it is giving me this as the suggested response. I'll directly update the block. I'll click update the block. I'll close it. All the values, you can see P, I, D, N values are here. It has already updated those values here. I'll press OK. And now if I run it, you can see, okay, this was the open loop one. This is the closed loop one. It didn't reach 1, but here you can see that it reaches 1 very quickly and it settles down very quickly, and the overshoot is much less. So this way you can actually use Simulink, and not just for step response, you can even have ramp response. So if you have ramp input, so suppose I just want to see what is the ramp input for this block, for this particular system. So this is the ramp response of the system. So there are actually many more functions of Simulink, and one of them is actually Symbscape, which we saw, means like in the course itself, for that inverted pendulum card balancing problem. And you can use Symbscape to model multi-body systems. So Simulink is a very powerful tool to use, and it's also very easy to use because it is graphical in nature, and you just connect the ports and add values and subtract values and see what is the response of the system. So this was on basics of Simulink, but there are many more examples which are available online, so I'll highly encourage you to look into those.